The cosmos is facing a serious problem, and the outcome could affect everything we know. Since 1929, when Edwin Hubble first demonstrated that galaxies are moving apart, we've understood our universe is expanding. This concept of expansion forms the backbone of cosmic history, from the initial Big Bang to the development of galaxies. Central to this is the expansion rate itself, a number called the Hubble Constant. For a long time, this value seemed settled, but astronomers are now questioning it. Are we about to witness a major shift in our understanding, or could our whole model of the cosmos be flawed? Let's delve into the growing crisis in cosmology and see how Hubble's landmark finding has become one of modern science's biggest puzzles. Throughout much of history, people saw the universe as relatively small. Early cultures pictured a flat Earth beneath a starry dome, with the sun, moon, and constellations moving overhead. By the 2nd century, thinkers like Claudius Ptolemy described a geocentric cosmos, with Earth motionless at the center and everything else circling around it. This view dominated for over 1,000 years until Nicolaus Copernicus, in the 1500s, proposed a revolutionary heliocentric model with planets orbiting the sun. Jumping to the 1700s, William Herschel mapped stars within our Milky Way galaxy, revealing its vast, disk-like shape. This debate was settled in 1923 by Edwin Hubble. Using the powerful Hooker telescope at Mount Wilson Observatory, he identified individual stars in the Andromeda galaxy. Among them, he found a special type of star called a Cepheid variable. By applying a principle developed by Henrietta Leavitt, which uses these stars to measure vast distances, Hubble calculated that Andromeda was about 900,000 light-years away. This was far too distant to be part of our Milky Way, proving conclusively that other galaxies existed. Hubble instantly and dramatically enlarged our cosmic perspective. He didn't stop there. Using the same method, he measured distances to 23 more galaxies, some as far as 20 million light-years away, concluding that millions of galaxies must exist beyond our own. Hubble's next world-changing discovery built on the work of Vesto Slipher. Starting in 1912, Slipher meticulously studied over 40 spiral galaxies. He knew that light from these distant objects could be split into a spectrum. If a galaxy was moving away from us, the spectral patterns would shift toward the red end, a phenomenon called redshift. Slipher found that nearly all galaxies showed this redshift, meaning they were receding. However, at the time, he couldn't accurately measure their distances or speeds. In 1927, Belgian scientist Georges LeMaitre proposed a theory, based on Einstein's relativity, that the universe was uniform and expanding. Without evidence, his idea was largely ignored. Hubble, unaware of Lemaitre's work, made his own observations from Mount Wilson. He confirmed Slipher's finding that galaxies were moving away, but noticed a critical new pattern. The farther away a galaxy was, the greater its redshift, meaning it was speeding away faster. This held true in every direction. Further observations showed that galaxies were all moving apart from each other, with redshift directly proportional to distance. This was the breakthrough. It meant the universe itself was expanding. Hubble announced this in 1929, and his work became the key evidence for Lemaitre's expanding universe theory, later known as the Big Bang. Hubble's initial estimate for the expansion rate, now called the Hubble Constant, was about 500 kilometers per second per megaparsec. This number was refined over time and has become a cornerstone of cosmology. We use it to determine the universe's age and size, figures that are vital for nearly all other cosmic calculations. To pin down the most precise value, astronomers primarily use two methods, but here's where things get puzzling. The universe operates on a beautiful mathematical order. Getting the numbers right is essential, whether you're calculating cosmic expansion or running a business. So what happens when the numbers disagree? You refine your approach. One way to measure the Hubble constant is by observing redshift in the modern universe, the same method Hubble used. This is often called the cosmic distance ladder, or late universe approach. It measures expansion as we see it now, billions of years after the Big Bang. As we gather more data on distant redshift, the measurement should become more accurate. 5 kilometers per second per megaparsec, significantly lower than Hubble's original figure. This newer technique estimates expansion by rewinding time to the very beginning. It relies on images of the cosmic microwave background, or CMB. This ancient microwave radiation is essentially a baby picture of the universe from about 380,000 years after the Big Bang. Predicted in 1948 and detected in the 1960s, the CMB wasn't mapped in detail until missions like the Wilkinson Microwave Anisotropy Probe in 2003 and the European Space Agency's Planck probe in 2013. These probes captured all-sky images showing tiny temperature fluctuations that would later seed the formation of galaxies and cosmic voids. Think of it like finding fragments after an explosion. If you then see a photo taken just as the explosion started, you can trace every piece back to its origin. Astronomers use the CMB snapshot to fast-forward the universe to today. 4 kilometers per second per megaparsec. You might notice this value is considerably smaller than the one from the Redshift method. This is a major problem. The expansion of the universe is a pillar of our standard cosmological model. The Hubble constant is woven into our most fundamental physics, from Einstein's general relativity to the Big Bang theory. This model, known as Lambda-Cold Dark Matter, emerged in the late 1990s and has worked remarkably well. A key feature is that scientists expected gravity to slow the expansion over time. Instead, they found it's now speeding up. This didn't break the model because we attribute this acceleration to an unseen force called dark energy. As the universe grows, dark energy's influence strengthens, causing galaxies to recede faster and making the Hubble constant increase over time. Both measurement methods are supposed to give us the current rate of expansion, so this acceleration isn't the cause of the discrepancy. How can we have one unified model with two different values for such a fundamental rate? This mismatch is called the Hubble Tension, and it's causing quite a stir in cosmology. It could mean our entire cosmological model is incorrect. It was assumed that as data improved, the two values would converge on a single agreed number. The problem is, with newer, independent measurements of redshift, the gap isn't closing. It's getting wider. One independent measurement used megamaser hosting galaxies. These galaxies contain molecules like water vapor that can amplify microwave radiation near a central black hole, creating a powerful maser signal. By precisely mapping these microwave emissions, astronomers can measure the black hole's mass and get an extremely accurate distance to the galaxy, 9 kilometers per second per megaparsec, with very high confidence. In late 2024, another study used data from the Dark Energy Spectroscopic Instrument to analyze Typeia supernovae in the Coma galaxy cluster. 5. Most recently in 2025, researchers used a method involving Mira variable stars, similar to Hubble's original Cepheid technique, and found a value of 73. All these recent measurements are in rough agreement with each other, but are far outside the error range of the Planck CMB measurements. Something fundamental seems to be missing from our cosmic understanding. Without a resolution, the foundation we use to interpret everything from galaxy formation to the universe's ultimate fate becomes unstable. 8-billion-year-old universe that will expand forever in a steady, predictable way. If the higher redshift value is right, then the universe is expanding faster than predicted. This could mean the cosmos is younger, perhaps only 12 to 13 billion years old, and that we are missing something crucial about the early universe, dark energy, or even relativity itself. Some scientists suggest radical adjustments might be needed to fix the tension. Proposals include dark matter that decays, dark energy that changes over time, or even modifications to the equations of general relativity. Such changes would force us to reevaluate our understanding of physics itself. However, another recent idea is gaining traction, one that might save our cosmological model without rewriting physics. All it requires is a little spin. Literally, a 2025 paper proposed that the universe might have a very slow rotation completing one turn every 500 billion years. This spin would be too gradual to have been detected, but significant enough to influence how space has expanded over time. Preliminary calculations show that introducing this slow spin into the model could validate both the Hubble constant values. It predicts a slower early universe expansion, matching the CMB data, and a faster present-day expansion, matching the Redshift data. These are exciting initial findings. With promising early results, it might be true for the entire cosmos. The authors stress this is just a preliminary calculation focused on the Hubble constant. The next step involves more complex models and simulations to test the idea against other cosmic observations. This hypothesis reminds us there is still much to learn. It's too soon to discard our entire model of cosmic evolution, especially when we might be on the verge of finding the missing piece. Even if this idea holds, it would mean a new, rotating version of our cosmological model, where cosmic parameters shift to fit a new reality. A major advantage is that it doesn't violate any known laws of physics. And it's a rather appealing thought. Not only is our planet spinning, and our solar system rotating, and our Milky Way galaxy turning, but perhaps our entire universe is, too, in a grand, slow cosmic whirl. If you found this journey through cosmic tension fascinating, help us explore more mysteries by subscribing to the channel. Your support through likes and shares helps us continue to bring these stories of discovery to you. And if this idea holds, it would mean a new, rotating version of our cosmological model, where cosmic parameters shift to fit a new reality. A major advantage is that it doesn't violate any known laws of physics. And it's a rather appealing thought. Not only is our planet spinning, and our solar system rotating, and our Milky Way galaxy turning, but perhaps our entire universe is, too, in a grand, slow cosmic whirl. If you found this journey through cosmic tension fascinating, help us explore more mysteries by subscribing to the channel. Your support through likes and shares helps us continue to bring these stories of discovery to you.